Hi, my name's Rosalind. I'm a professor at the University of Auckland. At a high level, I work on using mathematics and computing to understand how fluids move around underground, to help us understand how to produce energy from geothermal reservoirs and also from oil and gas reservoirs. I have degrees in engineering, but engineering draws a lot on, the kind of engineering I do draws a lot on maths, physics, computing. I work in a department called engineering science, so I kind of work at the border between engineering and science. I actually can't think of anything specific in terms of a specific moment, but it was always just kind of where I felt most comfortable. I love the power that kind of maths and science has to just help you understand the world, help you understand how it ticks, and just found that really fascinating in terms of what it could offer. Oh, I definitely agree that practicing mathematics will always make you better. And one thing I find disappointing in the way maths is sometimes taught in high school is students don't get to see how it's applied. They don't get to know, why am I practicing by rote this particular kind of equation, what it's used for, because it's taught in sort of isolation. So what mathematics is for me is actually not a bunch of equations and numbers on the page. For me, it's a language. It's kind of how I speak, how I think, how I problem solve. And mathematics at that point is really fun when you're using it to kind of understand the real world. But if you're using it to, continually practice problem 7 from chapter 3 that has no connection to the real world, then I can see why people find it frustrating and just give up. The other thing I'd say about mathematics is, no, there's no mathematics gene, but mathematics is kind of a confidence trick. What I see in young people who struggle with maths or say they don't like it is they just lose confidence with this. They get it in their head that they can't do it, and then they believe that they can't do it, and then suddenly all the kind of numbers and equations form a bit of a soup. So it is a bit of a confidence trick. You really have to back yourself. And there's a fascinating parallel for me between mathematics and music. So if you find someone who can read music and likes music and understands it and says they can't do maths, no way. Music has this incredible mathematical underpinning. So sometimes it's, those linkages pop up in strange ways. If someone says, I want to be a scientist and I'm not going to do maths, you are really doing it the hard way, because maths is, to me, it is sort of a universal language that unifies so much of science at the underpinning. So it's not impossible, but in certain branches of science, it is going to be a lot harder. But at the end of the day, it may be, ultimately a lot of science these days is done in teams, and it may be that you then have to sort your life out to, be a specialist in another area and kind of know when you need to be talking to someone who is better at the underlying mathematics to leverage that. The postgraduate degrees in nature are still very much a very individual contribution to the collective body of science. So a postgraduate degree is quite an individual undertaking, but you will have access to kind of other skill sets through supervisors and co-supervisors, and kind of being smart about how to leverage that is a really good skill. Undergraduate, at least in engineering, we're flipping things around. So we have what we call Systems Week, where in their final year, we cancel all their lectures for an entire week and say, you are doing a team project with a team of 30 people for the entire week. And the mind-boggling as that may be, the skills that are really going to help you flourish there are communication, teamwork, technical writing. So anyone that wants to be a scientist and sort of thinks, well, surely maths and physics and chemistry is all I need to know, I'd actually caution them and say no, because if you want to get your science to the point you can actually go and do stuff with it in the real world, you've got to be able to deal with clients, you've got to be dealing with people who are going to pay for it, whether that's government agencies, whether that's internal funding processes in a university or a government lab. So you actually really do need to be able to communicate and work with people. So we actually really emphasise that at the undergraduate level.
through?
Yeah, so Joe obviously went through university in a slightly different time. The systems work has been it's been around for about 5 years, and it builds up. So they go through a process of having projects that are kind of day long and smaller teams earlier on, and it kind of builds up to that. They have a compulsory paper in their second year on technical communication, and because we're a professional degree, this is something that our professional accreditation body, the Institute of Professional Engineers, really promotes to ensure our students have accredited status, whereas in a science degree that's a bit more freeform and you can kind of duck and dive and say, I just want to do calculus and quantum mechanics all day and not talk to anyone, you can get a BSc like that, but you can't get an engineering degree like that. You have to work in teams. I think it's well worth it. And does it take 100 hours? No, not necessarily. So I teach first year computing, and we teach a package called MATLAB, which has many sort of similar features to Mathematica. And within the course of 6 weeks, 3 hours lecture a week, 2 hours lab a week, so that's 30 hours in the first half, people are up and running in that and just doing amazing stuff, starting at zero. You can build animations, you can have MATLAB interacting with kind of scientific sensors or Lego Mindstorm's robots. You can do all sorts of cool stuff in way less than 100 hours. So to me, it releases you from all the drudgery. So, for instance, high school students, if I gave them 2 equations, 2x plus 3y equals 7 and x minus 5y equals 4. Off the top of my head, I don't even know if they have a solution, but a decent high school kid would, in their last couple of years, would be able to tell me if they had a solution. That's all very nice, but I tell people, well, on a good day, I solve 1,000,000 equations before breakfast. Today wasn't a good day, by the way. And to solve 1,000,000 equations before breakfast, I don't want to grind through all the same algebra. It's exactly the same process as solving 2 equations and 2 unknowns, but I don't want to do the hard work. So I teach my computer to do it. So getting fluent in something like MATLAB or Mathematica just gives you the capability to really change what you can do. Exactly. I mean, I think having access to a software platform like Mathematica or MATLAB just allows you to play a lot more what-if games with equations, to say, well, what if I did this? What if I did that? So the equations work and they have a nice, meaningful solution if I have these parameters, and then if I change something in it, then the equations go crazy, and instead of getting a solution that's a nice, smooth decay in time, suddenly my solution's oscillatory. What changed? And you can ask a lot of those sort of what-if questions and sort of see the physical effect of why it would matter, and then that kind of motivates you to learn, so what is it about these equations that's special, and yeah, flip the whole process around.
Your intuition.
Exactly.
Do you agree with that as a way of thinking about it?
Yep, exactly. I think people who do this kind of thing well are very intuitive, and obviously can't solve a differential equation in 3 decimal places in their head, but they know what the solution should look like, they know what it means physically, they just have that insight as to how it's going to behave. So software helps you build that intuition. Oh, absolutely. I mean, the kind of sort of electronics and sensors that you've got available to you now for minimal cost are really just mind-boggling, even compared to what you could access 20 years ago. So you can think of a question and literally, have a good shot at building your own little system to answer it and analyse it and really have some fun. So in my field of engineering, what's my superpower? Well, I guess it would be being able to think about what are the forces that move fluids through rocks underground, what are the things that really matter, what are the things that don't, because that problem is fascinating in that you can write down all the equations that govern it, but those equations have a bunch of parameters, they have a bunch of properties, rock properties, fluid properties, and these reservoirs are several kilometres down below our feet, and we can't even measure all the properties. So I guess my superpower, if you like, would be thinking about, well, what's important to measure, why is it important, what influence is it going to have on the solution, and really kind of just weighing up the value of going out and getting information. And the value, the information that we get in these problems, it can cost you $1 million, $10 million to go and drill a well. So, you really need to think pretty hard about whether you have to do that. Oh yes, you can see the kind of science that I enjoy out there in the landscape. I mean, the landscape is really just a snapshot in time of an Earth surface that's continuously evolving, continuously deforming because of the pressures in the Earth, continuously changing. I mean, Rangitoto out my window is actually very young. It's only about 800 years old. It's an absolute baby, and that's created by some of the same kinds of forces that create geothermal reservoirs. The role of New Zealand's Taupo volcanic zone is very, very special. I mean, geothermal, first of all, is a real taonga for New Zealand. It's very important culturally, spiritually for the people of the Taupo Rotorua region, and the kind of science I do helps predict how those systems are going to behave. We want them to be able to be produced sustainably so that there's geothermal for everybody's great-grandchildren. So Taupo helps New Zealand have an enviable record for production of renewable energy. So our electricity supply is 75% renewable, and the government are very, very proud of that. The international community are very envious of that, and that's something that geothermal helps us achieve.
Can you think of anything?
Well, I think you could do an experiment around what's called Darcy's law. So Darcy's law relates the rate at which fluid flows through a rock or a porous medium to the pressure change across that medium. So there's an experiment I can think of for less than $20. You'd actually just need to dive out to your recycling bin, grab some empty Coca-Cola bottles and fill them up with different kinds of things like sand or gravel, things that have different diameters, things that might pack closely together, things that might have lots of gaps in between. And then you can time, if you put a hole in the bottom, you can time, if the bottle's halfway full, you can time how long it takes to have fluid going through. And what you'll find is it will be different depending what you put in there, if you have gravel versus sand versus a mixture. And those kind of relationships between pressure change and fluid flow rate, because the pressure change is related to the height of the column of liquid that you fill it up with. Those same kind of relationships are what I do, but I divide reservoirs into hundreds of thousands of little blocks. So essentially hundreds of thousands of Coca-Cola bottle samples with different rock properties in each one.